Right now, your phone knows exactly which way is up. It knows when you're tilting it, rotating it, even when you're dropping it. And here's the truly wild part. There's no little person inside checking the angle, no camera watching the horizon, and no GPS satellite telling it which way gravity points. Your phone figures this out using physics so clever, so elegant, that when engineers first shrunk it down to fit inside a chip smaller than a grain of rice, it changed everything. Let me show you the invisible science happening in your hand right now. Pick up your phone, rotate it, watch the screen flip. Now, here's the question almost nobody asks. How does it know? You might think it's simple, obvious even, but what's actually happening inside that device is borderline magical. Your phone is constantly measuring forces you can't see, tracking rotations you don't feel, and solving physics problems thousands of times per second. And it's doing all of this with sensors so small, you'd need a microscope to see them. Before smartphones, if you wanted to know which way was up, you'd look around. You'd use your eyes, your inner ear, your sense of balance. Your phone has none of these things. Instead, it relies on something called an accelerometer. And understanding how this tiny device works will completely change how you think about the technology in your pocket. Here's where things get interesting. An accelerometer doesn't actually measure which way is up. It measures acceleration, hence the name. But here's the brilliant trick. Gravity is always pulling down on everything with a constant acceleration of 9.8 meters per second squared. So when your phone is sitting still on a table, the accelerometer isn't reading zero. It's reading that constant downward pull of Earth's gravity. And by measuring which direction that pull comes from, it knows which way is down, which means it knows which way is up. Now, if you're the kind of person who loves understanding how things really work, who gets excited by the hidden science in everyday objects, you're going to want to explore this deeper. In the description below, you can grab an ebook packed with 50 hands-on science experiments and fascinating facts, perfect for anyone who wants to see physics in action. It's the kind of resource that turns curiosity into understanding. But let's keep going, because the accelerometer is just the beginning of this story. So how does something smaller than a grain of rice measure acceleration? The answer involves one of the most beautiful applications of physics and engineering you've never heard of. Inside the accelerometer chip, there's a microscopic structure, a tiny proof mass, suspended by springs that are thinner than a human hair. When the phone accelerates in any direction, or when gravity pulls on it, this microscopic mass moves ever so slightly. I mean slightly. We're talking movements measured in nanometers, distances smaller than the wavelength of light. But here's where it gets clever. That movement changes the electrical capacitance between the proof mass and fixed plates around it. The chip measures these tiny changes in capacitance and converts them into acceleration data. It's doing this along 3 axes simultaneously, measuring movement and gravitational pull in 3-dimensional space. And it's doing it thousands of times every second, feeding that data to your phone's processor. Now, you might be thinking, okay, that's pretty cool, but what's so insane about it? Well, here's where the plot thickens. Remember, the accelerometer measures all acceleration, not just gravity. So when you're in a car that speeds up, the accelerometer detects that. When you shake your phone, it detects that. When you're walking upstairs, it detects that too. This creates a massive problem. How does your phone know the difference between you tilting it and you accelerating it in a straight line? Think about it. If you're holding your phone upright and you suddenly accelerate forward, the accelerometer feels a force pushing backward. But if you're sitting still and you tilt the phone backward, the accelerometer also feels a force. Same sensor reading, completely different motions. So how does your phone not get confused? How does the screen stay oriented correctly when you're in a moving car, or running, or doing literally anything other than sitting perfectly still? This is where your phone reveals its second secret weapon, the gyroscope. While the accelerometer measures linear acceleration and gravity, the gyroscope measures rotational motion. It detects when you're spinning or rotating the phone, and it does this using a completely different principle of physics. The gyroscope inside your phone uses something called the Coriolis effect, the same effect that makes hurricanes spin. Inside the gyroscope chip, there are tiny vibrating structures. When the phone rotates, these vibrating masses experience the Coriolis force, which deflects them perpendicular to both their vibration and the rotation. By measuring this deflection, the gyroscope can detect rotation rates around 3 axes. It knows when you're twisting the phone, when you're flipping it over, when you're doing any kind of rotational movement whatsoever. But here's where we get to the truly insane part, the part that justifies every bit of excitement in that title. Your phone isn't using the accelerometer or the gyroscope. It's using them together in something called sensor fusion. And this is where the engineering becomes almost impossibly clever. The accelerometer is great at figuring out which way is down over time because gravity is constant, but it gets confused by motion. The gyroscope is excellent at tracking rotation in the short term, but it has a problem called drift. Over time, tiny errors accumulate and the gyroscope loses its reference frame. It's like trying to navigate by only knowing which way you're turning. Eventually, you lose track of where you started. So engineers created algorithms that combine both sensors, using the strengths of each to compensate for the weaknesses of the other. The gyroscope handles quick movements and rotations because it's not fooled by linear acceleration. The accelerometer provides the long-term reference because gravity always points down. Together, they create a system that knows orientation with remarkable accuracy even during complex motion. Now here's something that will blow your mind. When you drop your phone, it doesn't know which way is up anymore. Think about that. During freefall, the accelerometer reads 0 acceleration. From the phone's perspective, it's experiencing weightlessness, just like an astronaut in orbit. The accelerometer can't use gravity as a reference because the phone is falling at the same rate as gravity is pulling. But your phone doesn't lose its orientation entirely because the gyroscope is still working. It's still tracking every rotation, every tumble. So even during that terrifying moment when your phone is falling toward the ground, the gyroscope is maintaining a rotational reference. Once the phone stops moving, the accelerometer kicks back in, measures gravity again, and the orientation snaps back to reality. This is the same reason your phone works fine on an airplane. Even though you're moving at 500 miles per hour, you're moving at a constant velocity. The accelerometer still feels gravity pointing down, and the gyroscope tracks any rotations. The sensor fusion algorithm doesn't care about your velocity, only about acceleration and rotation. But we're not done yet, because all of this raw sensor data is just numbers. Converting those numbers into the smooth, responsive screen rotation you see requires sophisticated software. Your phone's operating system is constantly running sensor fusion algorithms, applying filters to remove noise, using something called a Kalman filter to optimally combine sensor data, and making predictions about orientation. These algorithms have to be smart enough to ignore brief disturbances. If you tap the phone against a table, the software knows not to flip the screen. If you rotate the phone just slightly while lying in bed, it knows not to reorient because you probably didn't mean to. There are thresholds, time delays, and decision trees all working together to create an experience that feels natural and intuitive. And here's something most people never realize. Your phone is also using context. It knows when you're in a video call and locks the orientation. It knows when you're in a camera app and needs to respond faster. Different apps can request different sensor update rates and different orientation behaviors. The system is constantly adapting to what you're doing. Let's zoom out for a moment and appreciate what this means. The sensors in your phone, the ones that tell it which way is up, are the same fundamental technology used in spacecraft, drones, virtual reality headsets, and autonomous vehicles. The physics principles we're talking about, measuring acceleration and rotation, are how robots navigate, how planes fly autopilot, how satellites orient themselves in space. The reason this technology is in your phone is because engineers figured out how to manufacture these microscopic mechanical structures using the same techniques that make computer chips. They etched tiny springs, masses, and beams into silicon using photolithography. They turned a mechanical device into a semiconductor, and that breakthrough made it cheap enough, small enough, and reliable enough to put in everything. Now, you might be wondering, what about in actual space, where there's no gravity? How would a phone know which way is up on the International Space Station? The answer is both simple and profound. It wouldn't, at least not using the In true microgravity, the accelerometer reads near zero in all directions. There is no down, there is no up. The concept becomes meaningless, but the gyroscope would still work perfectly. Rotation is rotation, whether you're on Earth or floating in the cosmos. The phone could track its orientation relative to when you started using it, but it would have no absolute reference to say this way is down. Astronauts actually deal with this all the time. Their inner ears, which work on similar principles to accelerometers, don't function normally in space. There's no sensation of up or down, which is why space adaptation syndrome, space sickness, is so common. Your phone in space would be like an astronaut in space, perfectly aware of rotation, completely unable to sense gravity's direction. And honestly, that's beautiful. It shows the limits of the system and reveals what we take for granted here on Earth. We live in a gravitational field so constant, so reliable, that we build our entire sense of orientation around it. So let's bring this all together. Your phone knows which way is up because it contains microscopic machines measuring forces and rotations thousands of times per second. It combines data from multiple sensors using sophisticated algorithms that compensate for each sensor's weaknesses. It adapts to different apps and situations. It keeps working even when you're moving, even when you're accelerating, even in the brief moments when it's falling through the air. And here's the part that still amazes me. All of this happens invisibly. You never think about it. You just expect your phone to know its orientation, and it does every single time. That expectation, that seamless experience, is built on layers of physics, engineering, and software that took decades to perfect. The accelerometer and gyroscope in your phone are triumphs of science and manufacturing. They're the result of understanding fundamental physics, miniaturizing mechanical systems to microscopic scales, and writing algorithms that extract meaning from noisy data. Every time you rotate your phone and watch the screen respond, you're witnessing the application of Newtonian mechanics, the Coriolis effect, and advanced signal processing. The next time you pick up your phone, take a second to appreciate what's happening. That little device knows exactly where it is in three-dimensional space. It's measuring gravity with precision, tracking every twist and turn, and doing it all with components you can't even see. The science that lets your phone know which way is up isn't just clever, it's genuinely insane when you understand what's actually involved. And maybe that's the best part. We carry this technology everywhere. We use it constantly, and most of us never stop to think about the invisible physics making it all possible. But now you know. Now you understand the accelerometers and gyroscopes, the sensor fusion and algorithms, the microscopic proof masses vibrating thousands of times per second. That's the insane science that lets your phone know which way is up.